Okay, so last class I kind of left you hanging here on the cathode ray tube. And so now we're going to start looking at what is this cathode ray. And so Mr. J.J. Thomson did an experiment to figure out what this is. And he did this in the late 1800s, early 1900s is when this was completed. So here's kind of a diagram of my cathode ray. So you got your two metal electrodes, you have your power supply, and then your tube. So there's two options that the cathode ray could be. It could be some sort of charged matter, or it could just be light. And so he wanted to test to see what would happen. And so his theory was if it was light, then it should just go straight through. So if my cathode ray, here it is, it goes straight through. If it's light, it just goes kind of straight through. But he wanted to see how this ray would be affected if he put an electric field around it. So then he puts an electric field. So he places this electric field, he's got a positive side and a negative side, and he wants to see if this cathode ray is affected by this electric field. So if it's light, light is neutral. So it shouldn't be affected by a positive or negative at all. If it's light, it'll just go straight through. However, if it's a charged material, it will bend towards either of the electric fields depending on what the charge of the material is. Okay? So then he has the electric field, he turns it on again, and instead of going straight through, it bends. So what JJ realizes is it's not light. The cathode ray is just not simple light as we think about it. It must be contained of some charged matter. Okay, so it bends and it's attracted towards the positive side of the electric field. So now he knows, okay, I kind of have a feeling for what it is, and because of which direction it went, what it is composed of. So let's detail that on the next slide. So what he realized was that the cathode ray is made up of some particles, and their charge to mass ratio was negative 1.76 times 10 to the 8th coulombs per gram. Now, just to kind of put this into comparison, the charge mass ratio of a hydrogen atom is 9.58, so a positive number. Now, you don't really have to know what those numbers are, and it might be really hard. So let's just kind of go back and figure out what we've learned from this. Okay, so it bent, we know it's not light, and it bent towards positive. So what is attracted to a positive? A negative, okay? So positives are attracted to a negative, also this negative repels it. So I know that the charged material is going to be negative. All right, so these particles have a negative charge. Okay? Because the beam was deflected away from the negative and towards the positive electric field. Now, the other thing that he could figure out was he could figure out the mass. Not only does he have an electric field that is positive and negative, but he can make the electric field different strengths. So think about this, if we're deflecting it. If the thing that I'm trying to deflect is like a balloon, you can kind of like just flick a balloon, and when you flick the balloon, it moves. So it doesn't take a lot of force for you to be able to move the object. But say the thing that I'm trying to deflect is like a semi-truck. If it's a semi-truck, it's going to take a lot more force. So one of the things that he was able to do was he was able to vary the strength of his electric field. So he could start with a really strong one, see that it bends, and then keep going down until it doesn't really bend. It doesn't have enough force to push over here. So when he does this, he realizes that the electric field that was needed to be able to do this was very, very low. So if it was very, very low, what does that tell me about the mass of my particles? They're more like the balloon than they are the semi-truck. So that means that their mass is really light. It doesn't take much for me to deflect them. Okay? So now he realizes that they're negative charged, and then he also realizes the mass. The mass must have almost 2,000 times smaller than a hydrogen atom. So he can already have the mass of hydrogen atom. This is from some previous experiments. If you want to, you can go in and you can read about all this in your textbook. I'm just getting the highlights. There's another experiment called the Millikan drop experiment. You can read that one. That's also kind of a somewhat big one, but I'm just covering the highlights today. Okay. So what he discovered was this particle, its mass was 2,000 times smaller than the hydrogen atom. The hydrogen atom is our smallest. So he realizes that this is something much, much, much smaller. So it has a negative charge and it's really, really small mass-wise. Okay? So this is what he discovers these particles are. So what he determines is he's going to name this particle. And so he is the first one to name one of our 3 subatomic particles. So you're going to want to know most of what's on this slide. So he's the one to coin the electron. So I might ask you, who's the one that coined or found the electron? That's J.J. Thomson. Okay? So this is the first of my subatomic particles. So electrons are the particles found in all atoms. Subatomic, it's within the atom. Okay? My cathode ray was just a stream of electrons. It wasn't just light, it was charged matter, and it was just a bunch of electrons. The charge, you don't have to know this exact number. All you need to know is that electrons are negatively charged. Okay? And they have a really small mass. And we're going to compare this to the other 2 subatomic particles. But all you need to know right now is that the electrons are found in all atoms, they're negative, and they're really, really small. Okay, so since JJ discovered this, you might be thinking to yourself, well, what was the theory that he was trying to test? Remember, the current theory that was going on right now was Dalton's atomic theory. So now we need to say, okay, well, what was Dalton's atomic theory? So what was the first law for Dalton's atomic theory? His first law was that each element is composed of tiny, indestructible particles called atoms. So he said that the atom was the smallest thing. Well, Thomson just discovered that electrons are within an atom. So there's something that's smaller than an atom. So Thomson has already shown that Dalton's atomic theory isn't correct. So since Thomson has shown Dalton's wrong, he has to rearrange, rewrite, and develop a new theory. So let's look at JJ's new theory. So like I said, since the atom is no longer indivisible, Thomson's going to give us a new model. So Thomson proposes that instead of being a hard, marble-like, unbreakable sphere, so an indestructible atom that doesn't have any smaller parts, that was Dalton, Thomson says that there's an inner structure. So he's really focused on that first part of Dalton's theory. Remember, Dalton had 4 parts of his theory? He's really focused on the first part. Instead of it being unbreakable and indestructible, he's saying there's parts to an atom. So let's do the new theory. So Thomson's theory was the plum pudding atom. So this is his atom. And so we had Dalton's atomic theory. Now we have J.J. Thomson's plum pudding. Now you might be thinking, why is this called the plum pudding atom? And you might have no idea what plum pudding is or whatever. Atom. That's okay. I'll give you a real world example. So the story goes that Thomson one day was sitting trying to think about what he thought was the new model for the atom. And he was eating some plum pudding. And so while he was eating some plum pudding, he got the idea of what he thought the atom was. Okay? Now, since you're probably not familiar with plum pudding, I want you to kind of think about chocolate chip ice cream. So if you think of chocolate chip ice cream, it's mainly just the white ice cream, the vanilla ice cream, sorry. The vanilla ice cream with your little chocolate chips kind of spread out throughout. So vanilla ice cream, chocolate chips throughout. So that's going to be kind of what we're going to compare ours to. So what Thomson says is that his structure of the atom contains mainly negatively charged electrons. So his atom contains negatively charged electrons. Because remember, that's the only thing that has any mass. The only thing that he's discovered was electrons. Okay, so that's the only thing he's got. So that's the only thing that's in his model are some electrons. All right. Now we have to think about this. If I have a bunch of electrons, so think about like my chocolate chips, electrons are what? They're negative. So are they going to want to be close together? No, because we said if they're the same charge, they're going to repel. So these electrons are going to want to try to be as far away as they can from each other. But something's got to keep them within the atom. And so what he says is that there's going to be a sphere of positive charge. So it's kind of like a force field. You can think of like Jedi force. So this is keeping the electrons. So if we're thinking about our chocolate chip ice cream, so think about the vanilla ice cream as like a force field. It's not really there, you can't really eat it, it's just kind of there, and it's what's holding the electrons, my chocolate chips, in place. So my chocolate chips are randomly dispersed within my vanilla ice cream, which is my positive sphere of charge. So it's got to have a charge to balance out the electrons to keep them from repelling and to keep them in place. Okay? So my electrons are held in the atom by their attraction to a positively charged electric field within the atom. The other reason that I need it to be positive is because my particle overall is neutral. I mean, my atom overall is neutral. So if my atom overall is neutral and I have a bunch of negatively charged electrons, like negative particles, then I need something to balance it out. So they kind of do double duty. It keeps the electrons within the atom, and it balances out and causes me to have an overall neutral charge. So the strength, the positive magnitude of my sphere is based on how many electrons. So there's one electron, this would be a positive 1. There's 4 electrons, this would be a positive 4. And it's kind of how you can think about it. All right, so this is my model. So let's think about a little bit more of what we can assume based on this model. So let's think about the mass. What would be the mass of my atom? So I only have 2 things in my atom. I have a positive force field, a charged sphere, and I have electrons. So the sphere doesn't have any mass, so the only thing that has mass is my electrons. So the mass of the atom is due to the mass of the electrons. Mass of the atom is due to mass of the electrons, because they're the only thing in my atom. Second, the atom is mostly empty space. Okay, so remember my electrons, they're really small, so they're not going to take up that much space, but they can't be close together. So there's going to be a lot of empty space in my atom compared to where my electrons are. So atom is mostly empty space because I cannot have a bunch of my negatively charged particles near each other because they would repel. And also the mass is due to the mass of the electrons. All right, so that's JJ's plum pudding model. And so now somebody else is going to come up behind him and try to test to see if his model is right. And that is going to be Rutherford. And we're going to learn about Rutherford in the next lecture.